This is an oscilloscope JDR instrument model 2000 that I found not working recently and that I fixed. That it had a resistor blown and then a few capacitor that were leaky. And so I recapped most of it and replayed the capacitors, and it's now working nicely. I'm going to demonstrate its function. So it's a two-channel, very basic two-channel oscilloscope. The only interesting feature it has is component tests, which I'm going to demonstrate with a few components here. So resistors, a diode, a bridge rectifier, and then a few capacitors. And so for signals today, I'm going to use radio frequency oscillation signals generated by this signal generator. So multiple frequency band, you can control the amplitude, the frequency, of course, fine and band, and then you can also modulate the amplitude of the signals. And then the other signal I'm going to use is just the calibration signal. All right, so let's get started. Power button on. The light turns on. I grounded here both of my leads, so I should see a nice center point here. That's because I'm in XY mode. Let me go to time signal, and I'm gonna center my signals here. Right here for channel A, well centered. Channel B can be centered as well. So right there. And so let's go. Let's have a look at the signal generated by this generator right here. All right, so here, not much to see. Probably amplitude has to be cranked up. Oh, I was on B. I select channel A. I now see this shadow, which is the signal on which I don't trigger, and when I use the right amplitude, I get a nice trigger, so my signal is not moving anymore. I can change the trigger here, and so inside the window I trigger at different values, and when I'm outside of the window, I just lose the trigger. Okay, so this is for negative slope, so it's triggering at this value for negative slope. So we can see that here I start with a negative slope. If I change the value, I'm triggering higher with a negative slope. If I change the slope, I'm going to trigger at the same value, but for signals that go up. Let's do that. And right there, you can see that it's starting, at signals that go up. It's very hard to see because this particular wave is pretty sharp, but let's change we can change the time units here to see more closely. We can change it very sharply. We can change it continuously also with this adjustment here. And so now you can see the trigger, positive trigger at different values of your signal. And when you go too high, right here, I'm barely triggering at the tip. And if I go higher, it's moving all over the place. I cannot trigger on it. All right, so that's it for this signal right here. I can now go to channel B. It's still grounded, and it should show me a square wave from the calibration. Let's turn this on. We see two lines, and so I can adjust the amplitude to see it better. So now I can ask it to trigger on channel beats and adjust the time here, adjust the amplitude, and then adjust the trigger level, and boom, I lock my signal here. Can change again the time, discrete, continuous, changes, amplitude, continuous, discrete. Okay, this is all working. I can plot both signals together. Right now I'm triggering on signal B. This choice is here. So you see signal B is fixed, The calibration signal is fixed, but the radio frequency intensity is all over the place, showing this shadow. I can now use the intensity modulation to see what it looks like, and you can see that now my oscillation is all over the place, but we can see that there is a nice kind of periodic, I want to say, sine wave modulation of the amplitude. Right, when you can add the two signals, now it's moving all over the place. Let me remove this intensity modulation. Now we have a stable signal where we can see the ups and down of the low frequency calibration signal and superimpose to that very fast oscillations from the signal generator. And we can probably not see that, but I'm changing the frequency and the amplitude of the signal that is superimposed. So this is adding the two signals together. All right, so I guess this is all you can do with a two-channel oscilloscope. Let's now demonstrate the component test. So we have these two input here are connected to two leads. So you choose to ground both signals to set it up. All right, so this is a nice grounded signal. Then you put in X and Y mode. Okay, it's always good to center very well the signal when testing the components. So here I have a nicely centered signal. And so what the component test will do is that it's going to apply an AC current, 8 volt AC current, AC voltage, that will be current limited to 2 milliamperes. Okay, and so let me press this component test. So now you have this this curve here that we're gonna need to adjust, and this x-axis is voltage and the y-axis is current. So apparently I have a residual current through my lead connected here to the system, and I'm gonna adjust the scales. So essentially we should adjust to 2 milliampere per divisions, and then this will be our 9 volts. All right, so without anything connected, we have voltage that is generated but no input. But if I make a dead short, I should let the current flow, and so I should have an intensity. And if I do that, actually you see this 2 milliampere plus and minus flowing through the system. So let me just adjust this dead center so we can really test component accurately right there. All right, so open circuit is voltage only, closed circuit you have currents flowing. Let's try some resistors now. So I'm gonna need both of my hands, so I'm gonna just put my phone here. And so for a resistor, the relationship between U and I, the current and the intensity, is U equals Ri. So we should have a nice straight line whose slope depends on the resistance. And right here, I'm testing a 43 kilo ohm resistor, and I see a nice tilted line showing this U equals Ri relationship. All right. If I take a larger resistance, 150 kilo ohm, now I will be 1 over Ru, so it's going to be very flat. And this is what we see right here, barely moving, is this 150 kilo ohm resistor. If I take a very small resistor now, I'm much closer to a short in a sense, so I have I equals 1 over Ru, and so it's going to be a much bigger slope, and so that's what we see for 100 ohm. So 43 kilo was this intermediate slope, 100 ohm is this, 150 kilo ohm is this. Okay, let's look at a diode now. So the role of a diode is to block current on one side, but to let the current flow. I mean, for when current flows in the other polarity. So when you present an AC current, you should see current flowing for, let's say, positive tension, but not flowing for negative tension. So let me try this diode here. And right here we can see that the diode is open circuit for negative current and then is totally closed, so dead short for positive tension. So this diode is working. This is one polarity. I can now invert my lead and I should have current blocked for positive tension and flowing for negative tension, which is exactly what you see right here, the opposite picture. Right, so this diode is working, which is a good thing because it's a new component. Let's now look at a capacitor. So what's a capacitor? A capacitor is charging and discharging depending on the amount of electrons flowing through. So there's a differential equation between the intensity and the current, where actually the intensity is proportional to C capacitance times the derivative of the current. So my current is a sine wave. The derivative of a sine wave is a cosine. So actually frequency like omega times cosine omega t. And so we observe actually an ellipse where the two signals, intensity and current, have a phase shift of pi, so a quarter of a phase, and an amplitude that depend on the capacitance. So right here, my capacitance is 33 microfarad, and so we can see this shape for the curve. If I try a much larger capacitance, so 220 microfarad, now I'm going to see a squished ellipse because the voltage will be essentially divided by C, the value of the capacitance. And so we see this much thinner ellipse. We can also have a look actually at the signals. We don't have to look at them in XY. We can actually put it in dual mode and look as a function of time. Let's try and trigger on the signals that I'm showing here. Right there. Oh, maybe a little more here. Maybe. Okay, change a little my units. And so what you see right here is tension and intensity as a function of time. So x here, so is voltage. Change the focus a little more intensity. Right here is nice signals. So let me take the other capacitor that I think was a little better condition. All of these components were actually taken from, all of these capacitors were taken from the machine, and they were all a little tired. So I expect this capacitor was a little better. I expect the signals to be a little nicer. Still looking to trigger on them. Yeah, right here. So this guy on top is the intensity. This guy on the bottom is a very nice voltage sine wave. And so we can see a quarter shift, phase shift between them, but also a change in intensity right there. And so if I use another, the other capacitor, I should see a difference in amplitude, but not in phase shift, which is precisely what you see here, which prevents you from triggering on it right there. We can see that the voltage is much less, which corresponds to the ellipse being squished. All right, so this is a This is a basic but nice, I guess, functionality of this cheaply made oscilloscope. That was a lot of fun to fix.